oxidation of aldehyde. Since ketone cannot be oxidized, for this section, we'll specifically be looking at reactions involving aldehyde. First, these reactions could also be used as a qualitative, as a QA reactions for you to identify aldehyde in the A-level lab. So one of the reactions is to use potassium manganate, where we already learned that the aldehyde would decolorize the potassium manganate. Next is that the aldehyde could also converts the orange dichromate, which is Cr2O72- to green, which is Cr3+. Next reaction we're learning is actually your Fehling solution. Fehling solution make use of an alkaline complex Cu2+ ion. Why the term complex is critical? Because you can't have alkaline Cu2+, because if you have alkaline Cu2+, from O-level QA knowledge, you know that you will have precipitated copper-2 hydroxide. In this reaction, your Cu2+ complexes, which actually bind itself to a complex anion, what we term as tartarate ion, will actually reduce. So Cu2+ will reduce to form Cu+, which is your copper-1 oxide, which is red in precipitate. In the lab, the color of the copper-1 hydroxide looks a little bit more like Milo. So as far as aldehyde is concerned, aldehyde will then oxidize to become a carboxylate ion, primarily because the medium is alkaline. So it comes from a carboxylic acid since the medium is alkaline. So let us take a look at the half equations, just in the event that you're being asked to derive in the exam, which has been asked before in exam. So the first is that we're going to take Cu2+ being converted to copper-1 oxide. In this case, we'll put a 2 to balance the copper, and eventually we'll arrive at this half equation. And in the case of aldehyde, we will actually put a RCO-. Thereafter, if you balance everything, this will be the half equation. These two equations, if you add it, they will give you the full equation, which is this equation that is given here. At the A level, you must know how to derive these equations. Next, we take a look is ammonical silver nitrate solution, which is termed as Tollens reagent. Again, another reagent that can react with aldehyde. So they call it ammonical silver nitrate is because ammonical means that there's ammonia present. Ammonia actually bind by dative bond to the Ag+ to give you actually a complex ion here. So the Ag+ here is basically being reduced to actually form your silver, and the silver will coat around the test tube given, and hence the term silver mirror test. In the process, the aldehyde would also be oxidized to form carboxylate ion. So this is also a chemical test for your aldehyde. Before we move on to Iodoform reagent, what we want to conclude is that all these four reagents that's been used are used to test for aldehydes and not ketones, since ketone cannot be oxidized. However, we want to highlight to say that benzaldehyde is actually more stable than your aliphatic aldehyde. So it needs a strong oxidizing agent to be able to oxidize it. One need to know that Fehling solution is not strong enough to oxidize benzaldehyde, unlike the rest of the other three oxidizing agents, which are capable of doing that. Finally, before we hit to Iodoform test, we need to also highlight to say that Iodoform test is also an oxidizing agent, and similar to your Fehling solution and Tollens reagent, they are all alkaline in medium. However, Iodoform reagents is used to test specific structures of alcohol and as well as your ketone aldehyde. So let's take a look now. So this is a continuation from where we left off in terms of our discussions on the Iodoform test for alcohol. So a quick recap is that in the presence of iodine and NaOH, which are oxidizing agent, so the first thing that happens is the alcohol will actually oxidize to form your ketone or aldehyde, and from there, each of the hydrogen is then being replaced with iodine until eventually when they form Ci3, this bond will start cleaving, forming CHI3, which is a yellow PPT, and consequently, this will then becomes your carboxylate, given that the medium is alkaline. In our case, if you're studying the Iodoform test on ketone aldehyde, we're not looking at the initial step. We'll be starting from here. So in this part here, you will see that the only aldehyde that gives positive Iodoform test is none other than your ethanol, which is this. Also note that in terms of ketone, we know that you can have many other carbons here, but basically the ketone that can give a positive Iodoform test is your methyl ketone, because you need a methyl group that's bonded to it. At this juncture, it's also important for us to highlight that we may actually have a structure that looks like that, is able to give a positive Iodoform test, because in this structure, if you examine it carefully, this is CH2, which means the structure started off with this being bonded to the carbon. And therefore, what it means is that initially the first step, this will be oxidized. So this is not there. So once it's get oxidized and you obtain this, then you realize that from here, the hydrogen can then be still be replaced with iodine. So bear in mind, such structure still give a positive Iodoform test. So similarly, in the same vein, this structure would have tested a positive Iodoform test as well, because CHI2 now directly bonds to C double bond O. Finally, with that, let's take a look at the equation balancing. For equation balancing, we have 4655 for alcohol, as illustrated here. And then now we have 3433 for any ketone and aldehyde compounds. So the 3 and the 4 applies to iodine, then sodium hydroxide, based on alphabetical order. However, one need to note when 3433 and 4655 does not work. Let's take a look. In the case of why 3433 does not work, is say, for example, in this structure here, we know this can give a positive Iodoform test, but we also need to note that there's actually a carboxylic acid group inside. So the first thing that we do is that we will apply the 3433 rule first. However, we know that the carboxylic acid that's present in the product here will still be able to neutralize with sodium hydroxide. So therefore, because of this, we will now have an ensuing reaction where COH is now being neutralized by NaOH. And therefore, if we add these two reactions together, we end up with this final equation, and clearly the rule 3433 no longer applies. In the same vein, if you were to now take a look at an alcohol, and obviously this alcohol here can give a positive Iodoform test, so we apply the rule of 4655. In the same way that we explained earlier, we actually have a carboxylic acid group here. So we know the carboxylic acid will neutralize with your sodium hydroxide, so the ensuing reaction will be actually neutralization. After that, if we take these two equations, again, we end up with the final equation. And that's where the 4655 no longer applies. The final reaction you're going to learn on ketone and aldehyde is not an oxidation reaction. It is a condensation reaction of aldehyde and ketone. And you will find that this is a QA reaction that's used to test for aldehyde or ketone. So the reagent that's used is called 2,4-dinitrophenylhydrazine. Let's start off by introducing the structure of hydrazine. Hydrazine, the structure is as such. So this is the hydrazine structure. When it comes to phenylhydrazine, it means that you take a benzene ring and then you bond it to the nitrogen. Then, of course, the next two parts is the 2,4-dinitro. So the 2,4 is at position 2 and at position 4. So hence the structure 2,4-dinitro phenylhydrazine. Condition is to add con HCl and to warm or heat, and you end up with bright orange precipitate, provided you have a ketone and aldehyde. So this is the final compound. So in the exam, you must be able to draw the final structure. So take note, in this reaction, it's called condensation, because the two hydrogen from NH2 and the oxygen from your carbonyl group combines to form your water molecules, and in the process, the nitrogen actually has a double bond with your C. So in summary, in the exam, you need to draw the structures. You need to bear in mind that it's condensation reaction. It is not oxidation. Finally, all the reactions that we have covered in this section, maybe 2,4-DMPH, Iodoform, Fehling solution, Tollens reagent, all these reaction does not react with your carboxylic acid. Some will say it's possible to react with carboxylic acid. That's wrong. Because although carboxylic acid has a carbonyl group, as explained previously, carbonyl group is not a functional group. The functional group for carboxylic acid is COH, which means it does not react with your 2,4-dinitrophenylhydrazine. It does not react with your Iodoform. It also does not react with Fehling and your Tollens. These same conclusions can be derived for acid chloride, ester, or amide, meaning to say that any structures that actually has a C double bond O, but they could be either an acid chloride, it could be either an amide, or it could be either an ester. So none of the reactions will be able to take place.